Okay, so we'll be understanding a boosting technique today, that is AdaBoosting. It's quite popular in image prediction systems, and it's actually proficient in predicting the face of a person. You would have seen on Facebook images whenever we are uploading whenever we upload an image, we see squares coming off. I mean, the Facebook system automatically recognizes where is the exact face location in the photos, and if there are 3 or 4 people, it exactly points out their faces, putting a square across their faces. So adaptive boosting is the technique that is used to identify faces, especially in image processing. And the name actually, AdaBoost is the common name for this algorithm, and the name actually comes from adaptive boosting, because in this boosting technique, at every stage of this boosting technique, we adapt the errors that were made in the previous model or previous round. So this basically defines AdaBoost. Adaptive boosting or AdaBoost is actually similar to gradient boosting decision trees, but there are a few differences that we'll be going through towards the last of this tutorial. And as we already got to know that they are used especially in image processing plus face detection. And in general, if you ask me, in general, gradient boosting decision trees are used commonly, and if compared to AdaBoost, GBDT exceeds in its purpose and the types of and the versatility and the types of applications in which it can be applied. So AdaBoost is quite precise in identifying faces, and image processing is not used as commonly as gradient boosting technique. So having said that, let's move towards we will try to see how gradient boosting classifier itself is used in the sklearn to implement AdaBoosting. So we can see we are actually right now on the sklearn's scikit-learn's page, and we can see that gradient boosting classifier itself has a parameter called loss. Gradient boosting classifier has a parameter called loss, and if in this loss parameter we define the default value is deviance in the loss parameter, and if we use deviance in the loss parameter, it basically defines which loss function has to be optimized, and deviance in default means that logistic regression will be used. And if we use exponential, then that means that for loss exponential, gradient boosting recovers the AdaBoost algorithm. So if you're trying to implement the AdaBoost algorithm, you will have to use this gradient boosting classifier with the parameter exponential. So as simple as that. Now let's move to the geometric intuition. So we will try to first understand, because AdaBoost is not that commonly used, and I have already shown how the implementation of AdaBoost happens. So we will basically try to understand geometrically in the background how does AdaBoost work. So we are actually right now on the University of Pennsylvania page, and here the AdaBoost has been explained so clearly that it will be very easy for us to understand this. All the credit goes to University of Pennsylvania. We'll be just referring this item which is in the which has been opened for the public to read and study and understand. So we'll be using this model now. So a toy example from Safire's tutorial. So this is actually a toy dataset. We are considering a toy dataset here, and it's two-dimensional. It has some positive points in blue and some negative points in red, and we'll be using this toy model to train a decision tree with let's say depth equals to 1. Whenever the depth equals to 1, we called decision tree as decision stub, and we usually draw only a single line or hyperplane parallel to the x or y axis to separate our positive and negative, or separate our classes or labels. Here we have positive and negative points, so we'll be drawing a single line to separate them, since we are dealing with a two-dimensional model. So in the first round, okay, so this is our data set. As we can see, we have 5 positive points, and we have altogether 5 negative points, all distributed across this data set. So what happens in the adaptive boosting algorithm is that in the first round, when we train our model, what we get is our model function h1x. So in the first round, what we are basically trying is to draw decision stump to separate our positive and negative points. The first thing in the first round that will be done is we'll try to, using this data set D1, using let me use my, okay, using this data set D1, we'll try to we'll try to train our a model H1, and this model basically will try to create a decision stump which will be aligned parallel to the y-axis, and we'll try to first separate the positive points from the rest of the points. So we, using this data point D1, we have actually identified a function h1x, and using h1x, what we have done is we have created two zones. One is the blue zone in which we have two of our positive points lie, and on the right we have the red zone in which we have misclassified three of the positive points which should have been included with these two positive points, and we also have the 5 negative red points. So we can see that this model is not completely correct. It has its errors, and it also has 3 misqualified points. So for this model H1, we will compute the weights and the parameter values based on its accuracy and the performance of this model. And what we finally reach to is we calculate the epsilon value, or the error residual value, as 0.3, and we also calculate the alpha 1, which is similar to the lambda that we use in our decision trees. So we calculate the alpha value as well as 0.42. Okay, so what we can see is we have 3 erroneous points here, the positive 3 erroneous positive points here. We have only 2 positive points that were clearly classified. So what we will do is, to remove this error, we will adapt to another data set, say D2, which we will use in the next regression. This D2 will be similar to D1, but will be different in only one key aspect, that is the points that were misqualified. The erroneous points, these positive points that were misqualified earlier, will be given, exponentially high weighted, right? Will be exponentially high weighted to create D2. So the misqualified positive points from D1 will be upsampled with exponentially high weightage, so that their importance increases in the next round, and the next time we run our AdaBoost algorithm, these 3 points are also given importance to create a model that divides our positive and negative points. So this data set, this D2 data set right now at hand, it has all the points coming from D1, but it has the 3 positive points that were misqualified earlier. They have been given high weightage, and this D2 will be used as the training data set for our next round. So in the second round, as mentioned here, we can see we have the H1x. This is the H1, the first model that we defined. Then in this model, this is the H2 model that we are right now identifying. So what happens is, when we increased the weightage of these 3 points, these 3 positive points, when we increase the weightage, we can see that our model that was created next in the second round, it included these 3 points as well in the area of these 2 positive points that were identified earlier from H1. So the H2 model, what it did is it also included, along with these 2 negative points, it also included the 3 misqualified points. It has adapted itself to include these 3 highly weighted points as well. And at this point, in the second round, the D2 dataset becomes the input dataset for training another model function H2x, as we have already seen. And this model again creates, if we look closely, this model has again created 3 misqualified points which should not have been in the blue area. They should have been in the red area with the negatives. So the blue area should have only contained positives. So we can again see that we have 3 misqualified points. The next step is to calculate the parametric values or weights, as we did in round 1. We calculated the epsilon 1 and alpha 1, the residual error and alpha 2 values, and we will calculate this in the second round as well, epsilon 2 and alpha 2. And what we will do, we'll repeat the same process what we did in the first round. That is, we will increase the weightage of these 3 misclassified erroneous negative points. And this explanation is so good that they have clearly explained the things. We can see that the first two positive points that were identified in the first round, they have kept it smaller, and because the weight of these 3 points was increased as in the data set D2, they have increased the size of these 3 points. And now because these three misqualified negative points are going to be increasing their we are going to increase their weights, so the size of these three negative points has again been increased to increase the visibility of the explanation. So this is the second this is the third data set, actually D3, which will be given as input to train for the third round. So D3, what is the difference between the data set that was D2 and D3? Let's go up, we will see. In the difference between D2 and D3 is that the three negative points that were misqualified while the H2 model was learning, we have increased the weightage on those 3 points. That is the only difference. And now this D3, so this D3 will be used as the training data set for the third round. So okay, just summarizing right now, in the first round what we saw was these 2 points were collectively qualified, rest of the points were put in the red zone. Then we first increased the weightage of these three, we upsampled these 3 points with exponentially high weightage. So in the second round, what the function did, what the adaptive boosting did, it implemented a learning function H2 which included these 3 high weighted points. But what happened when H2 was implemented, again 3 negative points were misqualified, so we had to repeat the process, and we created in our data set we increased the weightage of these 3 negative points that were misqualified. Okay, moving on, in the third round, this is our primary our primary goal is to use the importance of these 3 misqualified negative points and adapt an algorithm and create an algorithm that adapts the earlier errors. That is what basically happens in AdaBoost. So our H3 function, it basically included the 3 upsampled negative points, and it created another zone in which the 3 negative points were kept in the red section and the positive points were in the blue section. Now coming to the final classifier, if we see at each of towards the end of each of the rounds, we have alpha 1 value, also we have a function H1. In the second round as well, we can see we have the H2 model, the base learner function H2, and we also have alpha 2 and epsilon 2, the residual error, as well as the alpha 2 parameter values, regularization parameter values. In the third round as well, we have our H3x, the model function, the third round's model function, which divided it in this way, and we also have the epsilon 3 and alpha 3. Epsilon 3 is the residual error, alpha 3 is the regularization parameter. We call it the parameter as it is used in as lambda is used in the decision trees. If you have studied, I'll be shortly making a tutorial on that as well. So the final classifier, so we have seen that we have 3 model functions right now, three learned model functions on different data sets, different in the term of the weightage that we gave to the specific misclassified points, and based on which the models were further created. So we can see the H1 model function divides the positive points, the 2 positive points, in this way. The H2 model function defines these all points in this way, it only keeps the 2 negative points on the right. And our H3 model function, it creates a stump in this way, which is parallel to the x-axis. It keeps all the 3 positive points on the upper portion and 3 negative points on the lower portion. But in H3 we saw that there were 2 positive points that were misclassified in the red region, and there was 1 negative point that was classified erroneously in the blue region. So what the final classifier does is it adds up the good parts of all the 3 functions. It adds the good part of all the 3 functions by, it not the good part, it adds the 3 functions to find out the final function, that is our final model function, that is our H, as shown in this diagram, which is equal to alpha 1 H1, alpha 2, these are the alpha values, alpha 1 H1. So the first model classified the 2 positive points over here, then we have alpha 2 H2, The second model classified the two positive points, the three misclassified positive points, and this is alpha 3 and h3. So you can see the final model was able to separate all the points clearly. So this line is your h1, this line is your h2, and this line is your h3. So this is how adaptive boosting works. You saw that we just kept on adapting to the errors or the misclassified points that were made earlier, and we kept on increasing their weights whenever they were misclassified, so that the next round, when the next model learns, it clearly identifies the last erroneous values, gives importance to them, and a function is created accordingly. So we kept on doing that until we were able to add all the models, all the learner models, and we were able to find the final classifier model in which we were clearly able to specify the points. So please like and subscribe to my video, and share it with your friends. I have tried to create an easy explanation, and I request you all to go through it once more if you are not able to do it completely. Thank you very much. Have a good